Yes, Joel?
So you're talking, the force you're talking about in there is the force exerted on the mass by the spring?
The force exerted, the work done by the force of the spring acting on the mass.
The force of the spring
acting on the mass.
So your direction there confuses me then, because if your spring's like this and your ball's on it like this, isn't the force going to be in this direction?
What's the spring doing? Here's the original length of the spring, right here. No distortion in the spring. And I have the spring here at this position. And isn't there some tension in that spring?
Yes.
It's pulling back this way. And then I'm going to go ahead and let the spring continue to move out here even further, and that force is just going to grow.
So your spring is being pulled, not compressed.
Yeah, but I'm not talking about the work done by the pulling force. I'm talking about the work done to the mass by the spring. By the spring. Okay. So we end up with this type of an expression for that. Now we'll turn these things around in a few days. You'll see them. They're actually going to reverse their sign in a few days. And I'll go ahead and use the word potential because you're already familiar. You've used it before in physics. So potential is the ability to do work. It's stored. Think of it as stored potential. It's like you have tremendous professional potential. Okay? And you're gradually putting more and more knowledge into yourselves so that you can be responsible, effective engineers someday. Same thing's going on here. When we allow that spring to get extended out here further and further and further, there's more stored energy in that spring, more stored potential in the spring. And then let's say we get it out here and then we let it go. What's it going to do? It's at rest here. I let it go. It's going to give up that stored energy as it accelerates back here, right? It's going to speed up as it comes on back here and give up that stored energy and transfer it into energy of motion, kinetic energy. And then, watch this, watch my hand, it's going to come back through the undistorted position and be really flying, right? Really moving. And then now, once we move back past into the compression phase of the spring, then what's the spring doing to the mass then? When you're in the compression phase, the force is now acting to the right here as this spring continues to compress, and the spring is starting to do what? Cause it to, the mass to decelerate, slow down. And eventually come to rest, and then it's got stored potential again, doesn't it? So if it's distorted, either in compression or in extension, if it's distorted, it's stored energy. So it gets back here to its maximum compression, and then it stops, and it starts moving back the other way, giving up that potential. And what's it going to do? Oscillate. That motion is a simple harmonic model. Simple harmonic model. Where its greatest speed is when? As it passes through this undistorted position. Its greatest speed would be at that undistorted position. Now, springs are not always linear. Matter of fact, they're only linear over a small portion of their range, probably, of distortion. Oftentimes you have overload springs in vehicles and trucks. And what that'll do is you start throwing concrete or something heavy into the bed of the truck, and what'll happen is normally you might have a certain suspension system there, certain type of stiffness in the suspension system, making it comfortable to just drive around looking sharp in your big fancy pickup. But then when you start loading it up with rock, you want it to be able to behave and handle that load well, and so it's going to compress those springs down, and then the overload springs will start to come into play to allow it to have greater carrying capacity. So it's all design. It's all design kind of stuff. Okay. All right, so that's the theory. I think we're ready to actually start working a few problems, and we have about less than a half an hour to work a couple problems out. Everybody still awake? Okay. Another question, Daniel?
It might take a while. I can ask it later, but a lot of us have done quite a bit of work in strength of materials with modules of elasticity. All comes back to the same thing.
Yes.
Say if I know that a spring is, say, reinforced steel, and I can look up
Yes.
the modules of elasticity for
Yes.
it, can I convert a K value for a spring to a module of elasticity and bring those back and forth?
Well, modulus of elasticity has units of like stress, doesn't
Yeah,
it?
there's an extra unit of length hanging out on the bottom.
Yeah. So what you have to do is you have to, now where this could play in, I mean, this gets interesting in the theory of elasticity. In theory of elasticity, you use things like modulus of elasticity to allow things to expand and contract. Not thermal, but I'm talking just elasticity under loading. Okay, so it might stretch, and you take the load off, and it might recover and return to it. All right, that'd be perfectly elastic. Okay. You could put things, engineering materials, in the elastic range. You could put them into that kind of loading, and the same kind of stuff would occur. The same kind of analysis would occur, and you could actually treat it in a simplified form like this. Now, it's going to get a lot more sophisticated, though, if you start talking about going into a vibration kind of an environment. And then you can actually start to create fatigue at the molecular level. And then you actually eventually can cause things to fail, even if you keep them in the elastic range and let them fatigue over time, through many, many cycles, oftentimes hundreds or thousands of cycles. So it's more depth. It requires more discussion in depth to talk about how you could use that modulus of elasticity and kick it over here into this stiffness, linear stiffness kind of thing, though. Okay. Design. They used to make stuff that would last forever. I remember a pair of Nike tennis shoes I had, Lava Domes I think they were called. Those things never failed. And I tried after a couple of years go buy another pair. I did get another pair, but then what Nike do? They stopped making them. Why did they stop making them?
They weren't selling enough.
They weren't selling enough of them. I mean, that people would buy them and they never wore out. I have I have a waffle iron that my grandmother gave me back when I was a kid. Brand new, she'd gotten it when she'd gotten remarried to my step-grandfather, and gave it to me in the box and everything. That thing still works. How many waffle irons can you buy today that would still work 5 years from now? Not very many of them. So what they do, now what about car doors? Opening and closing car doors.
They do that on car doors.
You can do that. I mean, they actually test those things through hundreds of thousands of cycles after they built the prototypes to test them to make sure they're going to hold up through the life expectancy of the vehicle. So there's lots of things you'll be doing in engineering where there'll be economic decisions that'll actually overpower or overshadow your engineering design work. Economic consequences. Related to that, before we start doing some work energy problems, I just finished watching a DVD that was made back in 2004 called The End of Suburbia. I would highly recommend it. I was thinking of offering it as an alternative to the reading that I've asked you to do this term, but I think I'm just going to ask you to sometime while you're still in college, watch that DVD called The End of Suburbia. It was made in 2004, and it will have an impact on you as far as you thinking about as you move through the remainder of your education and the career path that you might want to take. I guarantee that it'll give you some food for thought. So it's a very exciting time to be moving into the engineering profession. I don't think you guys can go wrong with doing what you're doing. It takes a lot of hard work, but there's tremendous opportunities for you out there in non-traditional ways, not ways that there's big changes happening. We already know we're past peak oil, and there's some big changes occurring in the social fabric of our society and the economics and the way that we move goods around regionally and internationally. So I highly recommend that, called The End of Suburbia. Okay, enough of that. Let's work a problem or two. Oh, I should say one more thing, and let's take a peek on this page real quickly here. I even highlighted it. You're probably going, oh man, I've been getting really good with F equals MA, and now we've got work energy to deal with. Well, what is work energy?
It's a scalar. Yay.
That's very good. It's a scalar equation instead of it being a vector equation. And that's kind of exciting. But it's another way of approaching. It's just a variation, isn't it? Because we started out with V dV equals ADS, and we just tossed the mass in there, and we're interested in what's going on along a path, and we came up with the work energy concept. So right here, advantages of the work energy method: it avoids the necessity of computing the acceleration and leads directly to the velocity changes as functions of the forces which do work. It's on page 163. Further, the work energy equation involves only those forces which do work, and thus give rises to changes in the magnitude of the velocities. Free body diagram, absolutely critical. Actually, down here, just to point that out, I even highlighted it. And if I highlight it in my book, that's probably fairly important. For a single particle, you should draw a free body diagram showing all externally applied forces. For a system of particles rigidly connected without springs, draw an active force diagram showing only those external forces which do work on the entire system. That's what they mean by active forces. Everybody hear that? Active forces are forces that do work on the system. Okay. I'm going to give you a hint, so when you get to these homework problems, this one would keep this problem that's assigned in your homework would keep you up at night unless I give you a hint. Because what a number of you will do is you will take to heart what I was saying about the work done is the component of the force that's in the direction of the displacement. And what's going to be troubling to you as you apply this load P here and this mass starts rising up here, so don't forget there's mg on here, as this mass starts to rise up, then the angle that that force makes keeps changing. So I've assigned this problem previously, and that's the reason I'm giving you a little word of caution, trying to save you a little time. Some of you will sit there and ponder, how do I write an expression and carry out an integration across that path because of that continual angle change, and the component of force keeps changing. P remains constant in this problem. So here's the trick. You want to know it, or you want to play with it first?
I like a challenge.
Yeah, I don't want it. It spoils it.
There's enough here. There's enough other problems to give you challenges. Let me go ahead and give you the hint. Okay, this P force is remaining constant. This chord length right here between the initial position to B is some length. When the object comes up here and whacks into this spring, this length now has changed. How much work is done by P?
When it's up against the spring?
Well, in moving the particle from here to here, how much work is done by P?
P times the total distance that will.
P times the change in length of this piece of cord. Okay, so the cord length was this originally. It's now going to be shorter. It's going to be this. And so that change in length times P. Think about how far out this P force is pulled. Isn't it pulled out? Isn't that P force pulled out by that change in length of that cord? And that's the work done by P. So you don't have to be concerned about the angle change there.
Well, that makes it too easy.
Okay? So it'll be much simpler for you. All right, let's go ahead.
On that problem though,
Yeah.
given those angles, is the block ever going to hit the spring?
Yes.
Okay, there's
Because
6
you have
inches.
to find
Okay,
the
got it.
stiffness of the spring when that block hits it. You can figure out how much stiff it is to make the deflection only 6 inches.
I didn't see the math.
Yeah,
I
and
didn't see
in the wording
dimensions of
here,
block.
I didn't describe the wording, but what we're going to do is we want the maximum deflection to equal 6 inches of the spring, which is going to place that pin right here, right there where this undistorted spring end would be.
Block is some
Yeah.
volume. Okay.
Yeah, that's good. Okay. Yes.
For, there's a term used, active force. Is the active force on that weight changing linearly from the initial position to where it hits the spring?
On that problem?
Yes. Does it drop off from
No, the active
the
force.
initial?
No.
It doesn't. So it drops off kind of. Okay.
You mean, well, the active forces on that are the weight of the body, mg,
Right.
downward,
And I'm talking about the component resulting from P.
and then P remains constant.
Right. But
So-
I mean the active component though along the rod, it's going to drop off obviously from the initial position to where it
Yes,
hits
and
the spring.
that's what I didn't want you to have to sit and struggle with.
Well, no, I was just thinking
Yeah.
of what it would.
Because right now, if that angle is, see that angle right in here initially is at the inverse tan of 3/4, that angle right there. So the P component is P cosine of inverse tan 3/4,
Right.
is that piece of force here. Now, when that cable gets up to here, P force is perpendicular and goes to 0. The component.
Gets you off.
Oh, I'm sorry.
You changed the book.
Oh, I did? Oh, yeah, I was on the wrong problem.
There you go.
There we go.
I was having fun here. Okay. Sorry. So what I was saying is this P force here remains 50 pounds, and initially its component is the cosine part of that P force that's along here.
Right.
That's
I-
fairly
that's the initial.
significant. When it gets up here,
It's
P
gonna
is
be
only
0.
pulling this way, which is perpendicular, doing no force.
Right. So it goes from some B cosine of that
P
angle
cosine
to
of
0.
this angle to 0.
Right. Right.
Yeah.
But I was just wondering if I wouldn't solve it that way. I was just wondering if it was linear or not.
No.
I'm not.
It's semi-soil or something.
I don't think it is.
Yeah,
And
yeah.
that's fairly sophisticated to try to work that out. Okay. Good questions. Why don't we take this problem? Well, the ones that I like are the ones that I've assigned. Oh, actually, they're all pretty good. Why don't we take this one? Right up here. 2 kilogram collar. Released from rest at part A, at point A up the top. Slides down this 60-degree guide. And has a coefficient of kinetic friction of 0.4. Calculate the velocity of the collar when it strikes the spring, and then calculate the maximum deflection of the spring. And we only have about 12 minutes to get this problem done. So I'm going to kind of move through it fairly quickly. spring. I'm going to grab my book so I can refer to it. We have the spring down here with stiffness K of 1.6 kilonewtons. I'm going to convert that right away so I don't screw it up. Times 10 to the third newtons per meter. It's going to travel, before it touches the spring, a distance of 0.5 meters. The coefficient of kinetic friction is 0.4 on the guide, and the mass is 2 kilograms. So the weight is then 2 times 9.81. So I think we have a pretty good sketch. Oh, what do I not have on my free body of the mass? Normal force, which is this N, and the friction that opposes the motion. And since it's dynamic, it's in motion, then this must be the friction force, which is mu kinetic times the normal. And the question's asking the velocity as it strikes the spring. So we want the velocity when the displacement is 0.5 meters. And then we're looking for also the delta max in the spring. So I think we have everything to do the problem now. So I guess we better get this normal force so we can work up these different active forces. So we have active, what are the active forces here?
Active forces will be friction and the force component of gravity.
Friction's active, and the component of mg that is along the direction of motion, doing work. Okay, so we know that the angle between the normal and mg is going to be this 60 degrees. So by summing forces perpendicular to this, sum of the forces perpendicular must equal the mass times the acceleration perpendicular to the incline. We have no acceleration perpendicular to the incline, so that's 0. Sum of the perpendicular forces is positive n minus mg cosine 60 degrees. Has to be then equal to 0. And so therefore the normal as expected is 1.2, 9.81. Cosine 60 is 1/2. So that's a normal force reading. Let's keep going. Forces that do work. Forces that do work. So keep in mind our concept. U equals delta T. Scalar equation, which we're getting excited about.
Is that 1.2 supposed to be 2?
Yes, thank you. I made a mistake up there. This is a 2 value, 2 kilograms. So therefore, we have 9.81 newtons of force, roughly 2.5 pounds of normal force.
That's the kilograms, it's 2 kilograms.
No, we're good. That's kilogram. That's okay. We're good. And now, the work done by the active forces. What we have is we have mg sine of 60 is the amount of mg that's doing work, right? And we have opposing it in the same direction along the path, negative 0.4 times that normal. And that combination of forces that sum of the two components of force is traveling this distance. This distance, 0.5 meters. So this difference in those forces is traveling 0.5 meters, and that has to be equal to the change in the kinetic energy, which is going to be 1/2, our mass is 2, times V at the 0.5 level squared, minus the initial kinetic energy was 0 because it began at rest. And not a bad idea, on your figure, you could write that it was at rest up here. Feel good? So over on the right side, the 1/2 and the 2 kilograms reduce out. And so all we need to do is take the square root of this value right here. And I don't know if they gave us these results in the book. If a couple of you, please punch that so we can confirm the value. Yeah, square root of that. Somebody else punch that. Somebody else double check, please. Okay. Now, we need to do the spring compression problem. Holler out if that value's wrong, or if you disagree with it. Now, we have to do the spring compression. Okay. We were interested in the maximum spring compression. So today, what I'm going to do is just go ahead and I want to do the problem from its initial position to its final position. Okay? Initial position to the final position. So if I do it from the initial position to the final position, then I'm going to have this work done by these two masses, or by the mass and the friction, is going to be our mg sine 60 degrees minus 0.4 times the weight, 9.81. Traveling, now watch this, a distance of 0.5 plus delta max. No, the friction remains on the rod all the way through the motion. So notice we have the unbalanced force, active force here, this portion, times the travel distance is the work done. And that has to be equal to the change in kinetic energy, which has to be equal to 0. The change in kinetic energy has to be equal to 0. Because it started at rest and it ends at rest after the spring is at its maximum compression. So what we do is we can solve this, and you can see that all it's going to be, if you distribute this out, this is a number. Actually, we should probably get this as a number right here. And keep in mind that this is a 2 times 9.81 right here. Sorry for being messy. Kind of rushing here. Everybody got it?
13.06.
The combination of these two? 13 point what? 0.6. And then that's times 0.5, which would be a half of that, plus 13.06 delta max has to equal 0. So what we're going to end up with then is dividing out that. Don't we end up with a half? Is that?
Yeah, that's what I got.
A half? Yeah, it looks like a half.
I get 9.0.
What? Well, I'm shooting for delta max here.
Is that for the spring?
The maximum displacement.
Delta max.
Where's the 1.6 included?
Tell you what,
We haven't hit
I
the swing
don't
yet.
trust that result from what I'm seeing here.
Yeah, I get
So,
like 9.04 centimeters because,
okay.
yeah.
So anyway, with the recording, we have to stop now. But this is going to keep it exciting for those of you who want to watch the DVD, okay? Is what we'll do is we'll pick up first thing next class session, and we'll wrap this problem up. And then I also want to generalize this so you can see what the behavior is as it moves through that displacement from zero displacement to delta max. Okay, that's it for today.